Okay, we're live. How about you? Okay, we're live. How about you? Fantastic. Good deal. All right. I made a few adjustments to the stream setup this morning, so uh, audio should be slightly better. I've swapped around the compressor, the noise suppression, so we should have less noise when I'm talking. Quality still isn't going to be great because the quality of the microphone in this headset is not fantastic. I also bumped up the text size in our text editors a couple of steps. Just noticing that, especially when in the lower quality stream settings, it was very hard to read things. So that should be slightly better this time. All right, so welcome back to the DX12 streams. Today we are going to do a lot of cleanup, some bug fixes. We're going to fix all the resource leaks that we have at the end of the frame right now, and we will look at handling things like adapter selection so that we can actually run on the discrete GPU in this laptop and not the integrated GPU. So, if we get through all of that, we are going to get rid of our lovely triangle and render a teapot instead. So that's exciting. I don't know if we'll get to that today. If we don't get to it today, we will get to it tomorrow. So let's get started. So first thing, which I believe is a bug, I'm not entirely certain it is, but we can check in the debugger once I explain. I think this is wrong. And the reason I think this is wrong is when you give an event a name, and then you create another event with that same name, it will return a handle to the same event. So in effect, we have three handles to the exact same frame end event. Now, we're getting away with it because if you remember, we never mind, I'm completely wrong. We're not getting away with it because the event only knows whether it's set. It doesn't know we're not setting a specific value to it. So this is a bug. I think the only reason we are surviving this bug is our GPU frame is fast enough that we are never waiting on more than one frame at a time. That's my assumption. So something we can do first is set a breakpoint here, and let's figure out whether we actually have the same event. Okay, interesting. we got 3 different handles. I don't know whether that means that we have 3 handles to the same event, or if we have 3 separate events. In any case, in any case, I don't think we need this name, and it makes me feel better if we don't provide it. So this should be more correct. It seems like it is. All right. There's another way to handle this, which is we don't actually need 3 different frame end fences. Not with how we're doing our swap chain. So the only time that you would actually need 3 separate fences for a triple buffer swap chain is if you, I don't know how to do this in DX12, but Vulkan has this concept of I think it's mailbox, where basically the GPU will, the API will hand you a frame index. It'll tell you you're on frame N. And normally you would expect that index, in a triple buffer case to be 0, 1, 2, 0, 1, 2, 0, 1, 2. However, in Mailbox, there are some cases where you're running fast enough on the GPU that you don't actually need that triple buffering. And the API will just hand you 0, 1, 0, 1, 0, 1, 0, 1, 2 occasionally, and then come back and forth. So for that, you would need a separate fence for every frame in that swap chain, because you never know what sequence of frames you're going to get out of it. But if we know that we're going to be handling swap chain frames in order, which I believe is the case here, because that's how we're handling this. I don't think that the API gives us any. The API doesn't tell us what frame we need to be rendering. So we could just have a single fence that counts upward monotonically, and instead of always waiting, we can check, hey, is the most recent completion on this fence greater than or equal to our frame index? With the last submitted frame index for this swap chain buffer, because that would let us know, okay, this frame has completed. This number always goes up. 64 bits, you will never overflow that. Like, it will take thousands of years to overflow. So you can basically synchronize all 3 frames with a single fence. I don't think I'm going to bother doing that right now, just to avoid more refactoring work. But it's a thing that we can probably do in the future. I don't know if it would actually be any faster, but it would be less stuff. Less stuff is always good. Right. So we fixed the event name bug. Yay, we've done the easy thing. The next thing is if we run and then exit normally, we still have all of these warnings from the DirectX debug layer. And these are because we are creating bunches of resources during our setup, and then we never destroy them. We didn't destroy them before because you have to ensure that the GPU is done with them before you can destroy them, and last stream I couldn't quite wrap my head around how to do that. I know how to do that now. It's amazingly simple, but we will do that now. So the trick is, we want to wait for idle. We just put another fence in the command queue and wait on it. Because that queue is guaranteed to execute in order. So if we insert a fence, wait on it, we know that everything that came before it is complete and good. Hi, Ruby. I assume you're watching. All right, so we'll have a wait for idle fence, and we will need another event here as well. This is not efficient if you wanted to have the capability of waiting for idle multiple times, which you would in a full renderer. You'd have this, you'd build these once up front and then not create them every time you wait for idle. But we only use WFI once for the moment. So we'll just copy our fence construction logic down here. Okay, so now we know that our GPU is actually idle at this point, or rather, we know that the graphics queue that we created is idle. Since the graphics queue is the only one that we ever submit anything to right now, that's all we care about. In practice, you might end up with, you have a graphics queue, and you have an async compute queue, and you have a copy queue, and so you would, if you wanted to make sure that the GPU was completely idle, you would have to wait for idle for each of those queues. But we don't need to worry about that right now. Because I put these in scope, they kind of have to be the first things that we destroy. So release fence. And close handle on the event. You know what I forgot to do? I forgot to actually signal this fence. That would be a problem. That's incorrect. Graphics queue. Let's see. Apologies for me being bad at programming today. I have been in shader land all week, chasing compiler issues because I'm always chasing compiler issues. All right. So we need to tell this about the event that we want to actually trigger. And you know, I don't type unsigned anywhere else. Let's not start here. All right. Release events. We close the handle. That should be good. Let's just test that we actually successfully exit. I didn't screw anything up. Okay, cool. So now we can bring back our cleanup code. I don't think this is complete, but it's a lot of it. I still don't understand why this thinks that this might be uninitialized. Sure, fine, whatever. So let's see what it still complains about. Interesting. All right, call report live objects because I don't understand what's going on here. Is this part of the debug layer, or is this? Oh. Do I really have to get two separate debug interfaces? Okay. I'll go ahead and do this because might be annoying, but like more uh, more debug info is always better. The header for this. Just say debug all. Okay. Oh, good. It's a separate library too. Good. Okay, I'm not sure that I can static link the XGI and use the debug thing since it's a DLL, which I assume means that it's like intermediate layer or something. All right. I don't feel like fixing up my linking stuff right now. We're just gonna figure this out. Oh. That's interesting. Clearly our wafer idle is broken because it's telling us we're releasing data that's still in use. I don't understand why. Is this like initialized one or something? I don't understand. Okay. That succeeded. No, this initializes at 1, at 0, because we tell it to initialize at 0. I don't understand. Oh. Because I started my event signaled. That's why. No. Okay. Um, anything useful in here to figure out what's going on? No. Okay. It's irritating because it tells me I have live objects, but doesn't tell me what they are. Reset our command allocator before we release it. I don't know if we need to, but that seems like a reasonable thing to do. I guess the obvious thing is that maybe I'm just not destroying things hard enough. So root nature probably needs to be destroyed. Can I destroy these in that order? Probably not. Let's see. Shader model we can probably get rid of. Let's just go through and destroy everything that we haven't destroyed yet. Destroyed with the bug player. No, that's a release method. Okay. Swap change should probably go away too. What? Shader by good is a memory leak, but it's not a resource in the sense that D3D12 actually knows about it. So I think we're fine there, right? I assume once you build the pipeline state, DX12 doesn't care about the bytecode anymore. That seems like the reasonable thing. blob. RTVs are just data. I don't think we need to destroy them. We don't destroy the swap chain buffer. Destroying the swap chain is what does that. Okay. We made any progress? Not really. Okay. PSO, there's events, and the end frame events. These do get destroyed. Endless gets destroyed. That's fully destroyed. That seems weird. Zero. Sure. This is just plain obnoxious. Like, at least tell me the type of thing that I'm not destroying. Like you've got a lot of things that have ref count 0, which really feels like not my problem. Am I just misunderstanding how this works in general? Yeah. Reference count on an object reaches 0, release must cause begin with this point for itself. Release pointer is the only outstanding reference. Implementation must free the object. So, like, why are there all of these ref count 0 objects, and why is it telling me that this is my fault? Okay. At some point, I will do the necessary build stuff to get the DXGI debug layer running. And then we will be able to figure this out, hopefully. In the meantime, I'm going to say that because I have wait for idle and I'm actually releasing things, I'm doing my part correctly. And we'll figure out how to make this stop later. Get this question mark. Didn't quite do it, but did something. So adapter selection. When we create the device, we pass in an adapter. So adapter is just a way of talking about the actual physical GPUs we have access to. Interface for GPUs we have access to. These can actually be virtualized. So just because you have access to, you might have if you actually have multiple adapters to the same GPU, if it's virtualized, I don't know. But like there are ways for this to happen that are not mapped one-to-one to GPUs. That's kind of irrelevant right now. All I want is to go through the GPUs on this machine and make sure that we're running on the NVIDIA GPU and not the Intel GPU. Because this thing has a nice fancy 3080 in it, and I want to actually use it for something. So let's figure out where we get our adapters from. This also needs a DXGI factory. Okay. Fortunately, we've got one of those. Adapters. Hmm. I think we want this one, not the other API. Um, um, just gonna have a fixed size array for now. You can have 16 GPUs. If you have more than 16 GPUs, it'll just cut you off at some point. Okay. So while we're going through this list, we will look at each vector in turn. Um, and we will be able to use this information to decide what adapter we want to use. If we did want to use the other one. No. So I think we can make the, so what I'm looking for is I'm looking for some way to figure out from this data, like, is a given adapter an integrated GPU or a discrete GPU? Because I want to use the discrete I want to use the discrete GPU if it exists. If it doesn't exist, I want to fall back to integrated. So I think we don't have any like direct way to check this. I mean, a cop-out solution is look for Intel, and if it's Intel, then it's integrated. But like AMD makes integrated GPUs as well. Intel has apparently started making discrete GPUs, so that's not correct. I think we can make the decision based on whether it has dedicated video memory. Because an integrated GPU should have unified memory with all of the CPU memory. So it doesn't have its own pool of memory that's on the other side of a bus. So I would assume this should be 0 for an integrated GPU. I guess what we could do first is we could actually just go through this list and print them. Printf because this is a wide chart, because of course it is. Um, uh, Never remember how to write a 64-bit integer. Bytes. May as well label them. Okay. All right. So okay. I stand corrected. Apparently, Intel integrated graphics cards now have dedicated video memory. Um, okay, we're just going to pick the device that has the most memory, the most video memory. That is. That's interesting. That's a lot more memory than we were allocating before. So if we go and check in Task Manager, it says we're using GPU 0. We're not using GPU 0. We shouldn't be using GPU 0. Let's keep an index here. Okay. Yeah, so it says it's using a vector of 1, which is the 3080, which is correct. But Task Manager thinks I'm using GPU 0. I mean, we're certainly doing a lot with it. So there is also 3D work on GPU 1. Okay. I assume what's going on here is there's the discrete GPU, but I assume that what's happening is we're routing the actual output through the Intel GPU, because I think that's what the Windows compositor is using. And we're in Windows mode, so we go through the compositor. So this is probably correct. I think we're actually creating on the good GPU, and then there's just an extra copy at the end of the frame from the compositor that takes it back to the other chip. Okay. We'll call that good. So now I want to take all of those per frame things, and I want them to be just in a structure so that we can, so that it will be easier to make sure that we don't like create 3 fences and 4 events or something like that. Like in practice, that's not going to happen, but it's cleaner to have a single-sized array rather than a bunch of arrays. So construct Here we will hold our ring fence. Uh, yeah, that's fine. Actually, no. We're just going to have an index here. For what buffer of the frame we're using here. Because swap chain wants to hold all of its buffers. We don't really want to have 3 different things holding various references to swap chain if we don't need them. Like this is the relevant data that we need to know per frame at the moment. Right, there's also the command allocator. Okay. Second thought. So index is kind of pointless. Okay. Can I create a command list without any? without a command allocator related to it. I'm just going to reassign it every frame, so I don't understand. I'd rather not have to do this. Looks like no. Just port over what we are already doing. This feels silly to me as well. Like, we already know how many frames we've sent out. Like, we don't have to ask DX12 about that. I'm just gonna have a frame counter out here. That's going to be 64 bits just because it. So otherwise, a high hertz GPU might actually like overflow your frame counter over the course of, a year. Doesn't matter in practice, but whatever. Launcher. I don't like frame index here. know, it feels like I'm just moving things around, and I kind of am, but when you have multiple things that have similar lifetimes in terms of usage and that sort of thing, bundling them into a struct makes just makes things easier in the long run. Interesting. Well, oh, right, yes. That little bit is important. Okay. Now, we can clean things up a little bit further. All right. Interesting. It still thinks this handle is null. It's not. Okay, I mean, sure. I do want to have a ring count constant just because I have threes all over the place and we may not necessarily want triple buffering all the time. Screw it and CLM. That is further insurance against any of these things getting out of sync. All right, we are hour and a half in. We fixed up most of the things that we wanted to do today. All right, let's start on something fun now. May or may not actually finish this today, but we'll start on. So we want to, right now, when we boot up, we are rendering a triangle, and of course it's very pretty, but like we want to actually render models, preferably models that are not like entirely defined inside of the shader. So we will start looking at building that system. If you are familiar with rendering, but not very modern rendering, this is going to look a little weird because, as I mentioned in earlier streams, we are not going to bind any vertex buffers. We will use input assembler to feed our index buffer, but nothing else. There are very good reasons for this. Part of it is on AMD, this is what ends up happening anyway. There's no actual input assembly for vertex data on AMD. It just injects code into the shader to do the loads directly. So that's what we're going to do. We're going to bind a buffer, and it's going to have, we're going to bind a storage buffer, and it's just going to have all of our vertex data in there. And it will be a very large buffer because when we do additional meshes, I'm going to render one today, but we'll have multiple later, they all go in the same buffer. And that's very intentional because that means that later down the road, we can we can render multiple meshes without having to actually swap out what buffers we have found. And that lets you do a lot more work creation on the GPU. So the GPU can tell you what your shortcuts are, rather than the CPU, which is useful for a variety of reasons, but is not possible in the standard input assembler way. At least it's possible, it's just more complicated, because you can't change bound state from the GPU. So you can't do like an execute indirect that then changes bound pipeline state. That's not a thing that's possible. Or at least it's not possible on PC. There are some consoles that can do it, but that's not something you're going to do. All right. So to begin with, we have this data folder, and it has this model in it. Yeah, this should work. Okay. So it has this teapot in it. We're going to load this teapot and render it, hopefully. So this is in OBJ format, which is a very simple text-based model format. Like, it's just literally lists of vectors. Parsing this is not hard. Parsing it is kind of annoying because text and floats and that sort of thing are kind of annoying to deal with. So we are going to use fastObj to get the data loaded, and then we will need to do some post-processing on it to get it in a format that we can actually put on the GPU and use. So I think I'm a bit out of practice with Git, but I think I can add this as a submodule. And that way we will get updates to this as they come in, if they do. But it's not. I think I copied this. And add. Okay, fantastic. Okay. Um, should now have this in here. We do. Awesome. It's kind of in an annoying place, actually. I want to be able to include this easily enough. Well, whatever. We can do some hacky things for now. We will have to define something to get this to actually do some implementation. Yeah. This is the standard single header thing. We have a header that has an implementation under define, so include that header everywhere. In one module, you define implementation. There's a single file to deal with, and it's pretty awesome. So make sure this actually builds. Not the correct thing to do, but I literally do not care. Okay. So we're going to need to do two things. We're going to need to write new shaders that will properly handle this stuff. We need to load the model, and we also have to work out buffer bindings, which I haven't done yet. That may be interesting. It's going to require us to do more complex things with root signatures, I believe. But I'm not sure. For now, we're just going to load the model, and that will probably be the rest of the day. So our geometries have they have an index buffer. We will use 16-bit indices. We could use 32, but we don't need them for this model. And in practice, we're going to be like any larger model that can't fit in 64K indices, you really want to split into multiple models. Because most hardware is, if hardware cares about your index size, it wants it to be smaller. And there are GPUs out there that want, that will take a slow path if you use 32-bit indices. Index buffer, need positions, normals, and actually have a back to class yet. It's a bit awkward. No, we don't need UVs right now. Here's our index buffer, here's our vertex buffer. For buffers, we actually de-interleave these because there are cases when, so say you're rendering shadow maps, you care about the position. You usually don't care about normals or UVs or tangents, whatever, when you're rendering depth only. And so by having your vertex attributes in different buffers, you can just not load position in the cases where you don't care about the other stuff. And because the other attributes you don't care about aren't in the same buffer, you'll never end up with, like, you're not wasting all of that cache space. So when you're loading positions, you're loading only positions. And when you're loading normals, you're loading only normals. And that just works better for most GPUs because they can load in a cache line, send all of those to vertex ports, and then immediately evict that cache line. So you end up with very short-lived cache lines, which is actually really good for streaming performance. So there are some cases with mobile GPUs where you don't want to do this, where loading from de-interleaved buffers is actually slower because you don't get that cache sharing. But on pretty much all desktop GPUs, this is the way to do it best. So I'm actually going, no. We could pad these out to vectors, but yeah, I think we should. You only need 4-byte alignment for vertex data, but 16-byte is better in a lot of cases. No, let's not bother. If we make that change, we will profile it and make sure that it's actually worthwhile. So now we need to load a geometry. Read the mesh, and we'll get a result that well, it's, you can go look at this. So OBJ files are a little weird in that normally you have one index buffer that references complete vertices. OBJs have different index streams for positions, normals, and text coords. So for example, if you have a model with a million vertices with unique positions, and they all have one normal, like the normal is always z up, and that's it. You would have all the indices for position, and then every normal would have the index of 0, so you end up not duplicating all that data, which, given that these files are text, is kind of a big deal. However, we have to basically deconstruct this when we go to actually generate GPU compatible meshes. The other thing that is slightly weird is the geometry in an OBJ file is not necessarily triangles. There will be polygons. I'm going to make the assumption that they're planar polygons, but they're not necessarily triangles. So what we're going to do is I'm going to follow this technique from Ruby about basically pretending that each of these faces is a triangle fan, which lets us triangulate on the fly. This is not the optimal triangulation, because triangle fans can create really narrow slivers, which are bad for rasterizers. They're also really bad for ray tracing, because you end up with an arbitrary number of triangles that all share a vertex, and so you can't make their bounding boxes not intersect. And so if you have a triangle fan in a ray tracing hierarchy, you end up having to check every triangle in that fan whenever you hit it, which is not awesome. So in practice, it doesn't matter. Good meshes, meshes exported from Maya or Blender should be triangulated nicely, or at least as nicely as they can. It depends on how nice the artist's mesh is. But we're using this data from Morgan McGuire's website, and I'm pretty sure that some of these have like quads and pentagons in them rather than just triangles. So we'll do the inefficient thing. We can make all of this faster later. It'll be fine. We also have materials and groups. Now, this will be useful later when we care about shading things and applying textures and stuff. For now, we don't care, and we're just going to ignore this. So we're going to, I don't actually know if this can return null. I kind of assume it can. Yes, it can. Mesh. Let's be honest, we haven't been doing much in the way of error handling up to this point. So we're going to iterate over faces. Mesh. We have to do this bookkeeping because we need to know where the first index of our face is, but it's less easy to map around than usual because we may have variable counts per face. So I'm going to actually screw that up one of these days, and then we'll have a real fun debugging session. All right. So we actually need to track our output index separately. Because we're going to generate more indices than we start with because we're triangulating on the fly. Or rather, we can. If it's already triangulated, this algorithm will preserve that existing triangulation. But if it's not, then we'll create extra. So I actually want to loop through once first because we want to know what our total index count is. So let's think about this. If the face has 3 vertices, or if the face has 3 indices, then we add 3 indices. If the face has 4 indices, we add 6 indices to the output. So it is 3 plus this index count times 3 times which I guess is base index count minus 2 times 3. Yeah, it's a chart strip. So with that, we now know how big our output index buffer should be. Why are you unhappy? I'm compiling in C++ just makes everything more annoying, and it's just okay. Right, but we need to be deduplicating our output. Okay, for now we're going to end up producing a wildly inefficient index buffer that doesn't reuse any vertices. We'll fix it later. It's not going to matter for what we're doing now. It'll be easy to fix later. But I just want something that works. So we're also going to use this loop to reswizzle the buffers for the different vertex data. Because while we'd use separate vertex buffers the same way that, or similarly to how OBJ does, OBJ has a different index list for each of them. And we need a single index list, which means that we're going to end up duplicating some of the data in theory, because we need indices to point to unique vertices, not unique vertex attributes, if that makes sense. The combined sum needs to be unique for us rather than just a particular attribute. So It seems super close. No, of course not. Okay. I don't care what Okay. That should be working. I don't know why it's telling me that I could have a buffer overflow here. Um, yes. Okay, that's into the community copy. Um, make sure that we actually output as many indices as we expected. Okay. Let's see if we can make this work. geometry, be in data models. Oh, that's unfortunate. It really feels like the sort of thing that should be a compiler warning. Like, I don't know. Right. So this is obviously incorrect because it means that our index buffer is just identity, which in turn means that we never actually reuse the text shading results, and we have bunches of data duplicated in the buffer that we shouldn't. But this is a small model. We are not in risk of running into any device limits. This is just easier, so we're going to do it this way. We will come back and make this work more reasonably in the future. All right. So let's actually go over to the shader side of things. So the mesh version of our shaders will be somewhat similar, but a little bit different. So We're still only going to take the vertex ID as input, but instead of computing our position stuff, we are going to load it from a buffer. I don't actually know HLS all that well, so let's figure this out. Make a structured buffer H plus all. Okay. There we go. This is what I want. So we will have a struct, call it vertex data. So we'll have float 3 position, 3 normal. Uh, hmm. Yeah, I might actually go back on my side and um, do an interleave for text buffer just because it would be simpler um, for this. So we have a structure. Sure, buffer for text data. Um, for text data buffer. So, this is input.id. Okay. And I'm going to need a projection matrix to get us to get from a position to a screen position. I need a projection matrix. But because I don't want to deal with all the weird row versus column major HLSL stuff, what I'm going to do is I'm just going to have our projection be 4 vectors. Because we'll be able to just turn this into a we can write the matrix multiply manually. It's not that hard. So cos x equals so these flip fours are rows of the matrix. So this should be easy enough. Right. Um, so now we need to compile the shader. We're going to keep the existing stuff working for now and expand on it here. This is data shaders mesh vert and pixel. Our pixel shader for now will do exactly what it does for the triangle. It's fine. We will actually we'll put the normal in the color just so that we have something to look at. Okay, so we have structured buffer and we have constant buffer. I assume I did that right. Yeah, that should be fine. Building. Shaders compile, they do not. So why are you unhappy? Helpful. We getting the output? No. And I'm not getting the error blob. So let's get the error blob out of this. That's fascinating. Um, understand. Oh, okay. Because I'm not naming the buffer. Um, it's kind of weird because it's not like you use this thing. Anyway. Okay. It seems to be compiling now. I actually think I'm going to leave it there for now. I will be back tomorrow afternoon. Hopefully we'll get all the buffer resources stuff squared away and get this rendering, and then maybe I'll come back in and fix this up to be this mesh loading to be less terrible. So yeah, thank you for watching, and I'll see you later.